Okay, a worked example that came up in the gravity support session questions recently, looking at how we use information about moons and orbits and projectile motions to give us information about mass of planets and radius of the planet. So the question that came up was question 3A, started off with that a moon had been discovered going around a planet, and that moon orbited at 250,000 kilometers, kilometers from center to center. Okay, so that moon is traveling around a circular motion around that planet. As soon as you see the term circular motion, you should immediately start thinking about centripetal force. Okay, we know the time period of that moon, T, is equal to 200 hours. Right, the first question, they also gave you some information about this, about if I fired a projectile upwards, as well. A projectile upwards, so vertical velocity upwards equals 20 meters per second, and maximum height reached by that projectile off the surface of the planet was 14.7 meters. Okay, so on planet. So on the planet, yeah, there we go. An object is fired upwards at 20 meters per second. It reaches a maximum height of 14.7 meters. All right. So the first question was all about find the mass, find MP. Now, what on earth is MP going to equal to? Well, for that, this isn't really going to help us find MP on its own. Okay. The first part of the information normally relates to the first question, and the second part of the information normally relates to the second question, as it does in this case. So what we have is this information here. We know that this moon is going in a circular path around the planet. Therefore, we know it must have a centripetal force acting on it. So whatever the resultant force is on this moon, it must be equal to mv squared over r. Well, what forces are acting on the moon? Well, it just so happens there is only one force acting on the moon, and it's the force of gravity towards that planet. So we know that force is equal to G, MP, mm, where mm is the mass of the moon, all over r squared. And the r here relates to the radius, the distance from the centre of mass of this object to the centre of mass of that object, which is 250,000 kilometres. Since that's the only force, it must also be the resultant force. Since the moon travels in circular motion, that resultant force must be a centripetal force. So the mass, since the object moving, the mass of the object moving, mv squared over r. Okay, the mass of the moon, we cancel those out. One of the radii cancels out. So we end up with the mass of the planet is going to be equal to the velocity of the moon squared times by the distance, the radius of orbit, divided by g. Okay, so that gives us the mass of the planet. We find out v because we know the time it takes. It takes 200 hours to go around one entire orbit, one circle. We assume the orbit is circular. We know the radius of that circle, so we use 2 pi r. Okay, you can work out v. If you want to use omega or anything else flash, you can, but that's the most basic way of doing it. The next question wants to know the radius of the planet. Well, the orbital time and all that doesn't make any difference now at all. What does matter now is this information here. So we know that on this planet, from the surface of the planet, if we launch something up at this velocity, it will reach this height. So at this height here, we know v is equal to 0. Well, we can use our suvat to work out the acceleration. It just happens the acceleration here is the acceleration due to this planet's gravity, so that is also equal to g. Well, we know g is also equal to g mp over r squared. Now this r, this is the tricky bit I guess, this r here doesn't relate to the radius because it has nothing to do with the moon anymore. This r here relates to the distance that the object is from the centre of mass. Well, the object is here on the surface, the centre of mass is there, right in the centre of the planet. That distance there, well, that distance there is known as the radius. Okay, the radius of that planet. So we know, you work out the acceleration, you say a is equal to g, mass of the planet, which you worked out earlier, r squared, and we know the r now is, the r now is the radius of the planet, the mass of the planet we got here earlier, and we can just work that out. Okay, and that's how you'd use that, that's how you'd answer that question.